Alright, hello class. So in this video, there's a couple of things I wanted to talk about regarding the monotone convergence theorem before we moved on to the next section. And it's one of those things that's just sort of interesting when you talk about real analysis on a whole, or on the whole. Okay, and what I actually want to look at, it comes from the book. There's an exercise in the book here. Here in exercise 2.4.4. So it says in section 1.4 we use the axiom of completeness, the AOC, to prove the Archimedean property of the real line. We want to show that the monotone convergence theorem can also be used to prove the Archimedean property without making any use of the axiom of completeness. Okay, then part B says, now use the monotone convergence theorem to supply a proof for the nested interval property that doesn't make use of the AOC. Now, here's what is actually very interesting about this. Is these two results suggest that we could have used the monotone convergence theorem in place of the axiom of completeness as our starting axiom for building a proper theory of real numbers. So this whole axiom of completeness as our very first axiom to build up real analysis, it didn't necessarily have to be the one we used. If we started, and instead of talking about sets and supremums, we instead started our discussion of real analysis on sequences, we could have instead used the monotone convergence theorem as our starting axiom and called it maybe the monotone convergence axiom, and then built up our real analysis from there, and then use sequences to help us define supremums of sets, and it wouldn't necessarily be the axiom of completeness anymore. If we were assuming that the monotone convergence theorem was true, we could likely use the monotone convergence axiom to prove that a supremum would always exist by basically creating a sequence of all the elements in the set that would be like increasing up to the limit, and then you would say that limit would be the supremum. Okay, so let's actually go about proving this. This isn't something I would necessarily give as a homework, but it is something I would like to look at. So in part one here, we're going to look at proving the Archimedean property without making use of the axiom of completeness. So just as a little reminder here of what the Archimedean property states, it essentially just tells us that for all x in the real, so for any real number, there exists a natural such that that natural is greater than x, or x is less than that natural. So how we prove this with the axiom of completeness is we did so with a contradiction. So what we did is we would suppose to the contrary. So suppose to the contrary that there exists an x in the reals such that for all n in the naturals, okay, that x is greater than or equal to n. Okay, so what this means, this implies that the sequence n is bounded and monotone. Right? Because what we're saying is that if the Archimedean property is not true, then that means there exists an x in the reals such that x is a bound on all the naturals. Well, that means if we took the sequence of all natural numbers, that it's bounded by x and 0, right? Each n is also greater than 0, so it has bounds on both ends. And it's monotone because, well, just by definition, 1, 2, 3, 4, 5, right? That's monotone. So, therefore, by the monotone convergence theorem, the sequence n converges. So let's let L be the limit of the sequence n. All right? So then we know that since n converges to L, for any epsilon, we can get the distance between, say, L and terms of the sequence as small as we want, provided we go out far enough. So since n converges to L, there exists, let's say, a capital N in the naturals such that the absolute value of n minus L is less than any epsilon we want. So let's just say it's less than 1. Okay, so there exists an n for any epsilon. So I'll just say there exists a capital N for any epsilon, but we'll choose epsilon equal to 1, just for simplicity, because what we're trying to do is get a contradiction. And usually when you're trying to get a contradiction, you just pick a particular epsilon, and then you try and get down to your contradiction with that. So typically we choose something like 1 or 1/2. All right. Then, and this is true, I didn't specify, but there exists a capital N such that this is true for little n greater than or equal to big N. Specifically, capital N minus L absolute value is less than 1. All right, so if this is true, this statement here is true for all little n greater than or equal to big N, it's also true for big N. All right, so if, let me call this statement up here star. This is just extra explanation here, but if star is true for little n greater than or equal to big N, then it's also true for just capital N. All right. Now this I'm going to mess with a little bit. All right, so this implies that, well, if the absolute value of n minus L is less than 1, that means n minus L is trapped between -1 and 1. All right, now I'm going to add L to all three, I keep wanting to call it sides, but all three pieces. So I have that L minus, L minus 1 is less than N, which is less than L plus 1. Okay, now I'm going to take a closer look here. And if I take this inequality here, okay, so this implies that I'm going to take this inequality and let's add 2 to these pieces. I could add it to all three, but really I just want to look at this. So if I add 2, that's going to tell me that L plus 1 is strictly less than N plus 2. Okay, so that means here I could actually put in less than n plus 2 here. Okay, so that means n plus 2 is greater than L plus 1, okay, which will be greater than L. All right, so n plus 2 is greater than capital N, so n plus 2 minus L absolute value must also be strictly less than 1. Okay, because the star statement I have here is true for any n greater than or equal to capital N. Well, n plus 2 is definitely greater than capital N. Okay, so that means this must be true. However, absolute value of capital N plus 2 minus L, well, this is going to be positive, and that's because N plus 2 is strictly greater than L. So if I were to move, and over here, some extra notes, from this piece here, if I move L over, I get 0 is strictly less than N plus 2 minus, okay, sorry, shift that down, but 0 is less than N plus 2 minus L. So this thing is positive, so we can actually drop the absolute value bars. That's just going to be N plus 2 minus L, and N plus 2, or is that over here? And this should actually, this is actually part of our proof here. Sorry if that wasn't clear. N plus 2 is strictly greater than L plus 1. So N plus 2 minus L is strictly greater than L plus 1 minus L, which is equal to 1. So we have that N plus 2 minus L absolute value is less than 1, and N plus 2 minus L absolute value is greater than 1. So this is a contradiction because we can't have that 1 is less than this thing, which is less than 1. All right, so this is a contradiction. And that will finish the proof. Therefore, the Archimedean property is true. Now, of course, we know that, but this is a proof using solely the monotone convergence theorem. All right, so let's look at part B now. We want to use the monotone convergence theorem to supply a proof for the nested interval property that does not make use of the AOC. All right, so let's set that up. Okay, before we do, I don't really want to rewrite all of the nested interval property again, but just to remind you what it says, if we basically create a set of nested closed and bounded intervals. So for each n and n, assume we are given a closed interval in here, a_n to bn, and assume that each in contains I sub n plus 1. Then the resulting nested sequence of closed intervals, I1, which contains I2, which contains I3, which contains I4, has a non-empty intersection. That is, this countable intersection of these intervals is non-empty. Okay, so we're going to try and prove this with the monotone convergence theorem. So when we prove the nested interval property, we definitely use the axiom of completeness because we use the fact that the supremum of a certain set definitely existed because it was bounded. What we're going to do now is instead prove the same property, but instead using the monotone convergence theorem. All right, so let's get started. Just by definition, we know that each I sub n is the closed interval a sub n / b sub n, and we know that it contains the next a sub n plus 1 to b sub n plus 1, which is our I sub n plus 1. Okay? Now, this means by definition, okay, an is going to be less than or equal to an plus 1, which will be less than or equal to bn plus 1, which will be less than or equal to b sub n for all n in the naturals. That just comes straight from the definition because each interval is contained in the next one. So if this is your in plus 1 is something like there. Now they could overlap, but here's your here's your an plus 1. Okay, so, and then here's your bn plus 1 and your bn. Okay, so this is true for all n. So if we consider the sequence of ANs, right? Just the sequence AN, by definition, this sequence is increasing and bounded. And it's bounded, well, every one of them is bounded by b sub 1, since all ANs are less than all the BNs, which are all less than B1. Okay, so AN is increasing and bounded. Therefore, by the monotone convergence theorem, AN converges. Okay, similarly, the sequence Bn converges. It's decreasing and bounded. Now, we may not need this in part of our proof, but I'm just writing it for clarity, I guess. So this is decreasing and bounded. Okay. All right, so suppose AN converges to A. All right, so let's suppose AN converges to A. So let A be that limit. I have a couple of propositions to make. My first proposition is that the AN is less than or equal to A for all n. Now, this is true since if there existed, say, an M such that A was strictly less than A sub n, then, well, every term of the sequence would be strictly greater than A for the rest of the sequence's life because the sequence is increasing, right? So then A would be strictly less than AM, which would be less than or equal to AM plus 1, which would be less than or equal to AM plus 2, which would be less than or equal to every capital M where capital M was greater than or equal to lowercase m. And this will not make sense because if the sequence is converging to A, but it's not allowed to get back down close to A again, we'll have a contradiction. So that's our first proposition, that all the ANs have to be less than or equal to A. They could all be equal, but they've all got to be at least less than or equal to. So they can't ever get greater than A. All right. The next proposition is that A is less than or equal to Bn for all n. Okay, so this one might be a little trickier. So this is true since if there existed, let me use M again, such that, let's say this Bm was less than A, right? So say eventually the B's cross over A. Now if I were going to draw that as a picture, right, so here's A. So for the picture for the other one, if one of the, so all the A's are doing this, if one of them crossed over, then they would all start crossing over, okay? Now, if one of my B's crossed over, say here, then all my other B's would be over here. Well, then my A's couldn't actually converge because all the A's are trapped below here, right? All my A's are on this side, so I wouldn't be able to get close enough to A. So that's just an explanation with a picture. So if there exists an M such that B sub M is strictly less than A, then AN will be less than or equal to Bm, which will be strictly less than A for all n, and the A's, or the ANs, could never get close enough okay? Or, instead of saying it that way, we know that the ANs converge, okay? So if this happens, then that means in between Bm and A, there would have to be more terms of AN, okay? Which can't happen, and that's because for any epsilon, right, for any epsilon, choose any epsilon, say this epsilon, there has to be a bunch of A's in here. But if Bm is here, I can't have A's here. Okay, so maybe that's a better way to describe why that's not possible, because all you'd have to do is choose epsilon to be the distance between Bm and A. Okay, and if you did that, you'd have an infinite number of A's on the wrong side of the B. Okay? So, based on these two propositions, A, the limit between A is between AN and BN for all n in the naturals. okay, which implies that A is in I subscript n for all n in the naturals, implying that A is in the countable intersection of the INs. And there we go. There's the proof. All right, so just to reiterate this important, or both of these important theorems, or properties really, we could actually prove by letting the monotone convergence theorem be our axiom instead of the axiom of completeness. All right, so that is the last thing I really wanted to show in this particular section. So I will go ahead and move over to section 2.5. All right, and I'll just get this one started. We'll really get into the meat of it later. But 2.5 is on subsequences and the Bolzano-Weierstrass theorem. I'm not going to write all that out just yet, but so subsequences are probably exactly what you would imagine. Although the way that they're usually, or the way they usually have to be denoted and talked about can be a little confusing. So let me give you the official definition, and then I'll just give you some examples. And you know, this official definition is to help with proofs more than it is for the understanding, which I guess is all of real analysis when you think about it. But if we let AN be a sequence of real numbers, or I'll just say be a sequence, and let n sub 1 less than n sub 2 less than n sub 3 less than n sub 4, so on and so forth, be an increasing sequence of natural numbers. Then the sequence defined in this way, where we take A, but we count it with this new subsequence of the naturals, A in 1, A in 2, A in 3, A in 4, A in 5, etc., is called a subsequence of AN, okay, and it's denoted in this way, basically by A subscript N subscript K. Okay, where K in the naturals indexes the subsequence. All right, so this may seem kind of obtuse as far as like how we're defining this, right? How we're talking about it. What you basically should know about subsequences is, I think of them this way. You know, here's the normal sequence, and this is where N is in the naturals. The subsequence, N sub K, well, N sub K, you can think of this as K is going through the naturals, and N is a subset of the naturals. So I sometimes think of this as, say, A sub j, where j is in some set capital J, which is a subset of the naturals. But the sequence keeps the same order. Okay, I think the quickest example is if you have a sequence A1, A2, A3, A4, A5, A6, okay? And you just took the even terms, right? Just A2, A4, A6, A8, etc. This is a subsequence. Okay? All it's doing is taking the even terms out of it and creating a new sequence with it. Okay? So it's much like a subset. I mean, it's basically the exact same thing as a subset, except the order matters, right? Same with the difference between sets and sequences. The order definitely matters with a sequence, whereas in a set, not so much. Okay. Then if we did A sub 2k minus 1, this will give us the odd term. So we'd get A1, A3, A5, A7. Okay, this is also a subsequence. Okay, so for this one, all it's doing is taking the odd terms and making a new sequence out of them. Okay, now, it doesn't have to be this cut and dry. Right, for example, if I had the sequence 1 over n, which is one of our go-to examples, right? 1, 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, etc. We could do just like we did before and do the A sub 2k, just all the even terms, right? 1 over 2k, which would just be 1/2, 1/4, 1/6, 1/8, okay, etc. But we don't have to. We could make another subsequence, and for example, let me start it over here. I could do like 1/10, 1 over 100, 1 over 1,000, 1 over 10,000, etc. Okay, so it's not so much that we can make a formula here. In fact, often we can't. All we're doing is just grabbing terms out of it. So here, the first term I would grab would be 1/10, and then I'd go out, you know, another 90 terms before I picked another one. Okay, so what's important is that it's only grabbing terms out of the sequence, the original sequence, and it's keeping the same order. Okay, and that is really important. For example, if I started doing this, if I did, okay, 1/10, then 1/2, then 1/3, then 1/10, then 1/2, then 1/3. This is not a subsequence. Of AN, because it has the same terms, it shares terms, but not order. And it repeats, right? So, for example, if I didn't repeat, but I was instead going 1 over 100, comma 1 over 99, comma 1 over 98, 1 over 97. This is also not a subsequence. It's the wrong order. So this is the wrong order, and it repeats terms. Okay, so if I made a sequence that basically just doubled every term as we went along, that would not be a subsequence. Right, so the sequence 1, 1, 1 half, 1 half, 1/3, 1/3, this would not be a subsequence. Because we're not holding the same order, we're not holding the same properties. However, if I called this sequence Bn, An, which is 1, 1 half, 1/3, 1/4, 1/5, etc., would be a subsequence of Bn. Right? Because what it does is it just grabs, all right, I guess I'll grab this first one, this 1 half, this 1/3. I'm only grabbing one out of all of them. So An would be a subsequence of Bn, but not the other way around. Okay. Okay, so essentially subsequences preserve the natural behavior of the original sequence. We'll say the behavior and order of the original sequence. So essentially, subsequences can only skip terms, but they cannot go back, right? So when you're going through to create your subsequence, you can go in order and you can skip, but you can't move back. You can't add terms. Right? They can only skip terms and move forward. All right, so this is actually a pretty good stopping point. I think I've thrown enough at you for one particular video. Some things to note, though. If a sequence converges, think about what happens to its subsequences. Okay, so that's what we'll be talking about next. So if a sequence converges, does its subsequences? I should also say, actually, I'm glad this came up. Note that a subsequence still has to be a sequence. So 1, 1 half, and you just terminate, this is also not a subsequence. Right? Because the subsequence still has to be a sequence. So just the element 1 can't be a subsequence because it also has a subsequence still has to continue on forever just like a normal sequence does. I completely forgot to mention that before. But that's another big property of the subsequences. They are still sequences. So if a sequence converges, does all of its subsequences? This is a bit of a spoiler alert. We'll get into this next time. But the answer is yes, definitely. And it all converges to the same thing. Okay? And so we will talk about that in the next video. Hopefully our brains will be nice and recovered from the melting they got today by then. And I will talk at you all that time. Cheers!